this video, I'm going to go over the textbook. As you got it in the back there. And try to cover some of the parts that are on the final because we have the whole textbook. Okay. We have questions from chapter 1 all the way to chapter 18. So we have to find. One is resistance, or circuitry, series circuit, parallel circuits, series parallel circuits, our basic components, which is P for power, E for voltage, I for current, R for resistance. Ohm's law, it's not on here. Basic Ohm's law, oh, where are the formulas? Okay, so we have the voltage is the E for the electric motive force, P for power, energy of work, that's a work that's being done, I for current, current is the amps, that's in. So one is the force, one is the intensity, and the other is the resistance. Okay, so Ohm's law can be expressed mathematically as R equals I over E. There it is. So this is the power wheel. Again, when we went through it, I didn't use the power wheel. I used Ohm's law. I used the two separate. So I showed it this way instead of that way. Make it easier. So E equals I times R, R equals E divided by I equals E divided by R, P equals I times E equals P divided by E, I equals P divided by E. The other one's P divided by I, I'm sorry. So these are different formulas. We have our circuitry, we have series and parallel. In a series circuit, in order to find the current, you have to find your total resistance. When these are in series, to find their total resistance, we just add them up. There's only one path of current, so the current would be the same through the whole circuit. So here is sample problem 1. So follow the circuit calculation to figure the circuit and voltage at each resistor, or during the voltage drop. Okay. In order to find our total resistance, in order to find our current, we have to add our resistors up. The 20 and 10 is 30, and 30 is 60. I have 120 volts force. I equals E divided by RT. RT is our total. So my amperage would be 2. There it is right there. So the current is 2. For my voltage drop, okay, right across here, voltage drop is ED, or ED is I times R. Okay? It's just a matter of multiplying. 30 times 2 is 60, 10 times 2 is 20, 20 times 2 is 40. 40 and 20 is 60, and 60 is 120, my implied voltage. Very simple. Okay, parallel. In the parallel circuit, each circuit, again, this is only a review, so you can always go back, and again, you got the text, this is the textbook. So in parallel, the sum of all resistors equals the current is the sum of all circuits. The thing is on a circuit, let me go back here real quick. On a series circuit, my voltage comes across here, goes down, comes across here, and then gets back to here. Okay, so The voltage is leaving the source, trying to get back to the source. There's only one path for current. Okay? Only one path for current. So when the voltage gets back to here, it's got to be at 0. So the current voltage drop equals the current times the resistance. The total current times the resistance. So here, again, this was 60 volts, this was 20 volts, and this is 40 volts. So 60 volts, that leaves me 60 volts, 20 goes across here. This 20 drops here, that leaves me 40. 40 goes across here, it gives me back to 0. In parallel, your total resistance would be less than your smallest resistor. Your total resistance would be less than the smallest resistor. Last one we added them up. Here we don't add them up. Okay? But because this is getting 120, this is getting 120, and this is getting 120, so the sum, the total current in the circuit is the sum of all branches. Here's 1 branch, 2 branch, 3 branch. So now I equals E divided by R. So 120 divided by 10 is 12 amps. 120 divided by 30 is what's that, 4 amps. And 120 divided by 20, 6, 12, 4, and 6 is your total sum. Okay, so here they did it. The first one is 12 amps. The second one is 4 amps, and the last one is 6 amps. So 12 plus 4 is 16, plus 6 is 22 amps. So this circuit has 22 amps. My total resistance, do they have it on here? No, they don't. So my total current is just a matter of adding all the sums. To find total resistance in the circuit, I get 120 divided by 22. That would give me my total resistance. The other way of doing it is R total equals R1 plus R2 plus R3 in the fractions. I'm not going to get into it right now. You remember that. I'm just giving you a little basic information. I'm limited on time. Here it is right here. Forming. So 1 over RT equals 1 over R1, 1 over R2, 1 over R3. You have to have a common denominator here. The common denominator would be 60. Okay. 10 goes to 66 times, 30 goes into 62 times, and 20 goes into 60. Add them all up. So my total resistance for the circuit would be 5.45 ohms. Okay. Here's a series parallel. I don't think I put any series parallel questions in here. I think they're all, but I could be lying. Current. This is still a series circuit. These aren't parallel to each other, but still they're in series with that one. So my sum would divide across here. So my total current would be the same, just like a series circuit. I have to squeeze together, make them one. In order, so here they're going to give me the resistor. Oh, okay, so R3 is 6 ohms, R4 is 12 ohms. You go through the formula. So my total resistance, let me go back. I'm just trying to see what they got. So this is a reciprocal because they have to find the common denominator. They flipped it back around. So 12 divided by 3, you flip it back around. 12 divided by 3 is 4 ohms. So this circuit here, total resistance of these two in parallel is 4 ohms. And then Number 1 is 1 ohm. R1 is 1 ohm. R2 is 7 ohms. So 1 plus 7 plus 4. That gives me a total of 12 ohms. Okay. Now I can find my current. Current equals ET divided by RT. My voltage is 12 volts. My total resistance is 12 ohms. So I have 1 amp. So I'd have 1 amp going across here because these aren't equal resistors. So the current would split up. And my voltage would be the same across each resistor. Okay, I don't think I have any questions on alternators. Again, you can go back and look at this, because it's going to be questions. There's 2 finals exams. There's 2 final exams. So one would be on one that I wrote up, and then one that comes out of the book. I don't think I'm going to use any of these formulas. Don't want to confuse anybody. True power and apparent power in the circuit. You might find 1 or 2. I just got a little note here. So again, apparent power and true power. So the apparent power it says, notice the power factor in a DC circuit. The product of voltage and current is the most AC circuits determined by the power and is a bit. The power factor is a ratio of the true power to the apparent power. It is expressed as a decimal and a percentage. Power factor may be 0 to 1%. Okay, so here's the one problem. Okay, so my amp meter reads 1, and my watt reader reads the other. Okay, so I got a AC source. This is my power. Here's my voltmeter. Here's my watt meter, and here's my amp meter. Okay, so my true power is whatever the watt meter is reading, and my apparent power is what my amp probe and my voltage. So amperage times voltage gives me wattage. So that's 1 watt form of wattage, and the other is what the meter is reading. Okay, this one is the utility meter. Utility meter is reading less than the other. So all of a sudden your power factor would be less than 100. Okay. So my true power is what my watt meter is reading. So my watt meter is reading 1900 watts, and you can see here the apparent power is my voltage is 240 and is reading 10 amps. So I got 24 VA. So that's 2,400 watts. So my power factor, I'm at 0.79. Okay, so a lot of times there's utilities find companies when their power factor is below 90%. Problem is they're paying more for electricity. Well, the utilities, like I said before, the utilities have to give you 2,400 watts, but you're only paying for 19 of it. So utilities are like, well, wait a minute, how can I make money here? On the other hand, you're saving money, but not really. That's why they put these things in where your power factor has to be higher. Excuse me. Next is a few safety things. It says completing the hazards. So always remember is when you're working on energized parts, as an electrician, you know me, I have, because I am a journeyman electrician, I am a contractor and everything else, and I've been in the trade forever. You know, so I can work on energized circuits. Why? Because I'm considered a qualified person. What is a qualified person? A person that knows, I mean, if I'm working on something that I know what it does. Okay, if I'm working on something that I ain't got no clue, I shouldn't work on it hot. But if I know how the machine works or whatever I'm working on operates, then I am a qualified person. Then I can work on it, energized. Okay, you're all just starting off. You know, so always remember, turn power off. That's it. Very simple. Turn power off. Safety note. The most important rule for preventing electrical accidents is to disconnect the circuit or equipment before doing any work. Turn power off. Disconnect it. Turn the power off. Lock it out. Tag it out. Okay. If you see any hazards, report the hazards. There's the lockout, tag out. There's a lock. There's a picture there. That was just the little bag that I got that I show off. Lockout, tag out procedures. Eye protection. Always wear a hard hat and safety glasses around construction areas. If you're not aiding an injured worker, stay out of the way of the people who are helping. So again, somebody gets hurt. If you ain't helping the guy, get out of the way. Let the people do who knows what they're doing. Call help. Let them take care of them. Yeah, but it's always wise, and I always recommend take CPR and take first aid classes. Tools. There might have been a couple on tools. You all know about tools. I'm just flipping through the pages here. You know, working on something. If you have to work on things energized, make sure they're insulated. This is an insulated tool. This is an insulated tool. This is not an insulated tool. Okay? These are not insulated tools. This is only for your, it's a cushion grip. That's an insulated tool. It says insulated, so it's labeled insulated, it's insulated. I did a good job on bending. Excuse me. Unfortunately, we couldn't get into the testers. There's a multimeter, hand probe, different brands. Okay, those are ideal. That's an ideal. This is a fluke. Collectible blueprints. Okay, so always follow your blueprints. I'm just trying to get through. I should have just gone to the front of the book here. Let me just go back here. Wiring methods. Okay, if you can't stay 1.25 inches from the edge, then you have to put protective plates. I think it was the next one. Your different types of cables. Supporting your boxes. 3 feet from a box if you're using metal conduit. 3 feet from a box if you're using PVC, ENT, flex, or anything that changes. But for most parts, rigid metal conduit, IMC, and EMT, 3 feet from the box and every 10 feet after. Rigid metal conduit, once you start getting into the bigger sizes, your gap can increase. Even though it can, I never do. So, conduit properties. So you can see that the outside diameter, the EMT is smaller than the rigid, but the inside diameter is the same. Except in IMC, you can get more wires than IMC because the inside diameter is less. Okay, I'm sorry. The inside diameter is more than rigid and steel. It's the same outside diameter as a rigid metal pipe, but it's thinner metal, so you got more room. There's a flex. Support requirements for flex metal conduit. No support is needed unless less than 3 feet for long leads. And always remember, if you've got a short piece, my part, I always say, pull the ground in. Okay? The code says you don't have to. INT, your supports are closer together. Why? Because it's more flexible. ENT, I'm sorry. Alright, cross section. Here we're going to need Table 5, Chapter 9, Table 5, Chapter 9, Table 4 in order to find wire sizes. So here we got a 2/0. It went down, that's a THW, went down, there's a 2/0. Approximate inches, 0.2624. They have 4 wires, they multiply it. They got number 6, they got 10 wires. Number 6 THHN right down here, multiplied by 6, and then they have the 10 number 10s. There's a THHN, THWN, I'm sorry, THWN. There's a number 10. Going back, they added them all up, so they have a total area of 1.77. Okay, now we go to Table 4. You find your conduits. Where is my sheet? So in the uglies is uglies. If you got the uglies or in the code book. So you got page 102, 101, 102, 103. If you have the code book, Table 4, and we have all the different conduits. So depending on what type of conduit you're using, this one is asking for copper, next cross-section wireways. Oh, what is the inside diameter? So we can only fill a conduit. The wireway must size be large enough that, oh, it's not conduit. It's a wireway. So we can only fill in 20% of the, we can only fill in 20% of a wireway. So we're going to divide it by 20%, and we need a wireway that has a 18.85 cubic inch. So therefore the wireway must have a cross section of 18.85 or larger. I'm trying to find the table. So here's our wireways. Here's at 100%, 75, and 20%. I should have scrolled to the bottom. Excuse me, it's getting a little warm in here with all these lights on. So, the cross-section area of all conductors in the wireway must be less than 20% of the cross-section area of the wireway. Splices and taps are permitted in the wireways, but must take up less than 75% of the cross-section area. So on that other one we had 8 point, so we will need an 8x8 box because we're under 20%. Okay, 20%, 6x6 is 36. 20% times 20% times 36 gives us 7.20. Okay, we were at 8.85, so we have to go to the next size up. Okay, looking at this table, an 8x8. Because an 8x8, that 20% is 12.8. Okay, one of the things, and I know I mentioned it then, I do not recommend using these personally. They do leave a sharp edge to the inside when you cut them. Okay, if you do use one, make sure you rim it out good. Last thing you want is an inspector to find, stick his finger to check to see if the conduits are ringed properly, stick his finger in there, and he cuts himself. Guess what? He's going to turn the whole job down. I saw it happen. Didn't happen to the job I was on. It was a job that somebody else did. I mean, they had other problems there, but blueprint says minimal size conduit, 3/4, and they used 90% of the conduit they used was 1/2 inch. The inspector walked in, he said, "Hey, wrong size conduit, take it all down." And then supposedly, and I was talking to the inspector, he says he walked in and he saw a guy using this tubing cutter. So he starts sticking his fingers in the conduits, and one of the connectors, one of the boxes, he stuck his finger in there real gently like, and sure enough he felt the edge. He goes, "All these conduits aren't reamed out. You have to tear all the conduits and ream everything out. Plus the conduits are the wrong size." So always be careful with that. If you do use one, make sure you ream it out good. Last thing you want to do is nick your wires when you put them in. And the problem is you're only going to see at the end. So if it's nicked somewhere in the middle, short's going to let you know there's a problem. Here we go. Conductors. Okay, these are different conductors. This is the properties of a conductor. Well, table 8, I'm sorry. Table 8. I can't read that and read to the bottom. This is table 8. So for most parts, we need to find out our AMG, our area, and then we also have copper coated and uncoated, and aluminum wire. Okay, so when we're trying to find the resistance of a wire, these are the resistance of a uninsulated conductor. Uncoated, that means there's no solder at the end of the pipe, at the wire of the wire. There's no solder at the end of the wire. A coated wire, that's one that has been soldered. So you have a copper wire, and they put this aluminum solder on it to make a connection, to hold the connection together. Okay, so it changes the resistance. Size of the wire, as you can see, starts off with number 14 and goes all the way up to 700 kc mil. When we're trying to find resistance of a wire, how many, this is a table we use. We can find the resistance of a wire with no electricity on it. How do we find it? Okay, come here, we have an uncoated copper. Okay, remember, it's always copper unless otherwise stated. Always copper unless otherwise stated. So you come in here, find a wire, and always use the number 12, solid. Okay, right here it's quantity. 1 would be solid, 7 would be stranded. Because you notice, once you get to size 6 and above, it's all quantity more than 1. You do have a number 8 solid. But when in a raceway, size 8 and larger, when in a raceway, size 8 and larger shall be stranded. Always remember that. When in a raceway, size 8 and larger shall be stranded. So we come over here. I got a piece of wire that's 50 feet long. What's the resistance of that wire? Number 12 solid, coated copper, ohms is 1.93. This is for 1,000 feet. I don't have 1,000 feet here. Let me just find it. 1.93. Okay, so I got 50 feet. I get the 50 feet divided by 1,000. I get 50 feet divided by 1,000. That equals 0.050. Now I get this, multiply it by 0.050. And that would be the resistance 50 feet of wire. What I do with my calculator? 1.93 times 0.050. So that 50 feet of wire is 0.965. That's a resistance of the wire. That is a resistance of that wire at 50 feet. Okay? Using table 8. For most parts, uncoated copper. This is per 1,000 feet. And it says it up here, there. Coated copper per ohms, K feet, 1,000 feet. So the resistance is for 1,000 feet. I don't have 1,000 feet of wire, I only have 50 feet of wire. Code requirements. So there's on the bare conductor. Did I miss something? I knew I missed something, but I just can't think of it right now. It's always copper unless otherwise stated. Temperature limitations. Okay, so when you go to table 3, 10, 15, 16 in the code book, get my code book over here. Okay, so you have the 60 degree, 70 degree. And then it says temperature limitation section 310.15.A3 of the code prohibits the use of any conductor in any manner where its operation temperature will be greater than that of the designated for installation type. Further, different conductors are not to be associated together in the way that could cause limiting temperature of any conductor to be exceeded. So what it's talking about is, you don't want to get some TWs with some THHNs and put it in a hot area, because the TW can only handle 60 degrees C, compared to the THHN that can handle 190 degree. Okay, so the temperatures are different. Conductor markings. You have your that's the markings on the conductor, maximum voltage, proper letter designation, and everything. For grounding, over here is this conductor identification by color. If it's a grounding, that's green or green with a yellow stripe. Grounded, it's a white or gray. And then in ungrounded, which is a hot, is any color other than white, gray, green, or green with a yellow stripe, or a bare conductor. When there's spice, it says equipment ground conductors that are insulated must be insulated solid green or green with yellow stripe of size 6 or smaller. Okay, so if you're sized any wire 6 and smaller has to be identified by color on the insulation. Size 6 or smaller has to be identified by color on the insulation of the wire. Once you get above size 6, like you get to number 4, I can use white tape as a grounded wire. They're all black. Well, I've got one of the wires that's going to be blue. I can use blue tape, green tape. I know I got a red. This is high voltage tape, insulated tape. But I got the other colors there somewhere. Okay, once it gets so above size 6. Allowable opacities, 310/16. Okay, so it says 3 aluminum type THHN conductors. Again, these ratings in 310/15/16. B16, I'm sorry. The allowable opacities. You got copper and you have aluminum. It's all dependent on the insulation. This is what I was talking about. 160 degrees C and 90 degrees C. I said 190, but it's 194 degrees Fahrenheit, 140 degrees Fahrenheit, or 60 degrees C and 90 degrees C. So you don't want to mix the wires up because, like say here, the number 10. Here it's 30. Here it's 40. Okay, depending on what type of thing. You know, the code says because of these asterisks, the biggest OCPD I can put on a 14, 12, and a 10 is a 15, a 20, and a 30. 15 for a 14, 20 for a 12, 30 for a 10. Once I get above that, number 8, TW is only good, or UF cable is only good for 40 amps, as a THHN can handle 55. I can't load it to that. I can use that number for derating the wires for voltage drop, not voltage drop, temperature corrections and adjustments. Okay, so maximum here I can load it as a 50. Capacity correction factors. So here's talking about correction factors. One conductor, 3, 10, 15, B16 through 19. I'm trying to find the table real quick. So here's my correction factors. 3, 10, 15, B2A. Okay, knowing the ampacities, what is the temperature? Okay, so go back here real quick. I'll use that number 8. THW. Okay. THW is right here. That's a -2. It's a 75-degree wire, does 50 amps. I'm putting it in a 95-degree Fahrenheit area. Okay. This ampacity is 3 current carrying conductors. This ampacity is for 3 current carrying conductors in a raceway. If I get more, I also have to do adjustments. The first I'm going to do the correction factor for temperature. Okay, 50 amps, 95 degrees. I said it was a 75-degree wire. Come up to 95, 0.94, 0.94. This wire can handle 47 amps. Okay, now I go in there, and this is from 310, 15, B2A. Okay? Then it's 310, 15, B. The next one. Where's that other one? Oops. There it is. Okay. So let's say I got 5 conductors. Okay. This 50 amps is in. 3 current carrying conductors in a raceway. I got 5. Okay. 4 through 6 is 80%. 5 through 7, 70%. 10 through 20, 50% on top of this. So I want to multiply it by 0.80 times 0.80. So the maximum capacity of the number 8 wire is 37.6 amps. 37.6 amps. Okay? So adjusting, temperature corrections and adjustments. Again, you have sample problems here that you can look at, and that is page 95. Okay, voltage drop. Let me erase this. Here, my biggest breaker I can use is a 35 amp breaker. As long as it's not a feeder to a panel. If it was a feeder to a panel, I can bump it up to a 40. But if it's feeding a branch circuit, 35 amps. That's it. Because I corrected the wire from 50 amps down to 37 amps. 37.6. Well, I can't go up. I have to go down. Because I can't exceed the rating of the wire. The rating of the wire is only 37.6 amps. Okay. Using the same thing, I got a conduit. I'll do it both ways. The way it has it here and the way they show it in the ugly. I like using the one in the uglies. Where's my cloth here? I like using the ones in the uglies because that's the way I was taught. Back in the late 70s. That's the way I was taught, so this way, but we'll show it this way because that's in the book. Then I'll show the other way. Okay? Voltage drop. At the number 8 wire. Let's say I had a circuit. Went out, and it's 140 feet away. Okay, it's 140 feet away. Let's say this is 40 amps. I need a wire that can carry 40 amps. Obviously, I can't use a number 8 because a number 8, just with the temperature alone, it doesn't help. It's at 37.6, I think it was. 37.6. Voltage drop. Book has it VD. I don't like using the VD. I like using the ED. 2 times L times I times R divided by 1,000. I'm going to do it this way first. If it was a 3-phase, I'm going to say this is single phase. So this is a 3-phase. If it was a 3-phase, it'd be, instead of a 2, it'd be 1.732, which is the square root of 3. Okay? Single phase is a 2, 3-phase. We use it. I got a 40 amp circuit and all says 240 volts. Single phase. Okay. I'm going to use that number 8 again, just to have a wire size. THW. (95° C). Five total conductors. Maybe we got a circuit feeding something else. Alright. So we got 2 times 140 times our current is 40 amps times R. Let me go back here real quick. Table 8. Okay. And the reason I use this, okay, now we got to use that stranded, coated copper, uncoated copper, number 8. Did I pass it up? Number 8, uncoated copper. And then this number, so it would be 2 times 140 times 40 times my resistance. My resistance is 0.778 divided by 1,000. ED equals 8.736. Well, what is my allowable voltage drop? 3%. Remember, 3% from the last overcurrent protection device to the thing. So from the last overcurrent protection device to where you're going, 3%. 240 times 3% equals 7.2. Okay, we're losing too much voltage. This is just on the wire being too small. Okay, now we have, on top of that, we have to do the corrections for the temperature and here. So obviously we know that wire does not work. Okay, so we did the voltage drop. Trying to find a towel, but I can't find it. Okay, so I'm going to leave that on there. I'm going to use a different color. Okay, so the formula is 2 times K times L times I. To save time, I'm just going to use copper. Cu 12.9. 2 times 12.9 times 140 times 40 amps. Go to table 8. Circular mills for number 8 is already on here. And number 8, they're both the same, 16.51 divided by 16 by 10. Because we didn't use exact K, these numbers are going to match. This number and this number are going to match because I'm using an approximate. Always remember is circular mills times resistance divided by 1,000 would give you the exact K. 2 times 12.9 times 140 times 40 divided by 16 by 10 equals 8.75. It's pretty close, not much off. So you're still at 8.5. You're still at almost 9 volts on both of them. But your voltage drop is only 7.9. Voltage drop, if we use exact K, it would be 0.778 times 16510 divided by 1,000. So my exact K, instead of using 12.9, if I were to use 12.84478. So if I were to use that number instead of that number, it would have been exact. It would have been exact. Times 2 times 140 times 40 divided by 16,510. Okay, yep. I got the same exact number. Okay, so I just added everything in. I changed that to this, and I got the same exact number that I got here. Okay, in this formula, the way the book has it, we're doing, here's my, oh, it doesn't have a size. It's giving you a size. Alright. The voltage drop. Next one is box sizing. Oh, that's what I forgot. I'm sorry. I almost forgot. So here's a problem that they're using for voltage drop. So I guess you need to practice. There's two ways of doing it. If it's a three-phase, the 2 changes to 1.732. It doesn't change with either one. Again, the next one is conduit capacity. Wires that you can get in a conduit. Okay. So in order to find the wire size, we need to use Table 5. Chapter 9, Table 5. You had it in one of the handouts. It's here, part of it is here, and some of you have the ugly, so you can find it in your uglies. When we fill the conduit, if we're doing only one wire in a conduit, we can go to 53%, 2 wires 31%, and over 2 wires we can use 40%. Well, why is it less on 2 wires? Well, more than likely you're going to pull more wires into it. That's why it's less. So here they're showing 112 TW and 1 number 10 and 3 number 8s. So it came over here, the conduit. You go to Table 5. Oh, what is the thing? It's 40%, so I need over 2 wires. I don't know what that. This total conductor area is 1.442. See sample problem 6-7. Go back a bit. So here's 6-7. So they got the number 12, 1. It came up here. There it is. There's a number 12, 0.0133. They had 1 number 10 and 3 number 8s. And number 8s is 0.0366. Multiply that by 3. The other ones, they added them up, so they had a total. Okay. And they went to Table 5. They are using rigid metal conduit. They found the rigid metal conduit, Article 344. They came down. Guess what? They got more than 2 wires come across. They were at 0.144. So that is a 3/4 inch, it looks like, because a 1/2 inch is 0.125. Okay, well, that's one. Is conduit sizing. Table 4, Table 5. You have tables of that. The other is box sizing. Okay. Once we size it, let me go back. Okay, always remember, it's got to be flush with the wall. So if you got a combustible wall, your distances, non-combustible wall, 1/4 inch, combustible wall, flush. If you got straight pulls, 8 times. If you got an angle pull, this is an angle pull. And gives you the conduit to there. It's 6 times. Okay. LBs, everything falls the same way. They're under the same existence. box sizes. Once you get all your wires, wires counted, you can pretty much find what type of box you need. When you go into the plastic box, these are all metal boxes. You go into the plastic boxes, it changes the sizes. Now you have to look at the box itself, because the code book only gives us these are all metal boxes. When we're multiplying the number of wires in the conduit, how many wires are going in, and our multipliers. So we're going to use this cubic inches. So 14 gauge is 2, 12 gauge 2.25, number 10, 0.5, number 8. Let me get to the problem at the end. So here's how do you count the wires. Excuse me. How do you count the wires? If a wire enters a box, if a wire enters a box, you get counted. So here I got a wire coming here, a wire here, and a wire here. That's 3. Okay. If a wire comes in, and goes out, there's no room or anything, that counts as 1. Okay. If it comes in and a loop is left, okay, counts as 2. So if you leave a loop so you can make connections down the line, that would count as 2. If it goes straight through, it only counts as 1. Okay, bonding jumpers aren't counted. So like they say, if it doesn't come into the box and it doesn't leave the box, you don't count it. So here's the pigtail. You don't count that. Our yokes or devices count as 2. If you have a large yoke, like a 50 amp plug, a 30 amp plug, those count as 4. Okay, so it'd be a double. Clamps, hickeys count as 1 of your largest wire. Conduit hubs do not count. The conduit hub and the lock knob do not count. Okay, no matter how many grounds you have coming in, they count as 1. On services, always remember lateral, underground, overhead when it's overhead. Both a service drop, service lateral. Try to get this done here. I covered box sizing, conduit sizing, ground sizing, wire size, voltage drop. Wire size, I covered that. Series, parallel, service types. Swimming pools we just did, so always remember swimming pools, your fans, how high they got to be, or anything else. Motors, I use the voltage. I use how do you size a circuit. Okay, output of a motor. So here's the question here. It says, what is the maximum output of a motor rated at 30 horsepower with a service factor of 1.25? Okay, all you got to do is get that 30 multiplied by 1.25. Maximum output is 37.5 horsepower. Okay, that's a very simple question. I was going through it, and it just got some of the regular stuff that I talked about. Voltage drop, wire sizing, conduit sizing, box sizing. And remember, 6 inches. You have a conduit. You have wires going into a box. How much wire you're supposed to have? Minimal 6 inches, free clearance. I'll talk about the services. This is the majority of the stuff that's on this. I think I eliminated some of the other stuff because there was too much problems. Tomorrow I'll have a Zoom. So again, see this video and make notes of anything that you might have a question with. Ask them tomorrow in the Zoom meeting. Alright, y'all have a good night. See ya.